Hi guys, today we're going to take a look at question 9 of the 2016 exam paper 2. Okay, so data on earnings were published for a particular country. The data showed that the annual income of people in full-time employment was normally distributed with a mean of 39,400 and a standard deviation of 12,920. So straight off the bat, before we even look at part 1, let's write this down. So normally distributed, so immediately we're thinking of the formula z equals x minus mu all over sigma. And our mean mu is equal to 39,400. And our standard deviation sigma is 12,920. Alright, now on to part 1. The government intends to impose a new tax on incomes over 60,000. Find the percentage of full-time workers who will be liable for this tax, correct to 1 decimal place. Okay, so let's try and visualize this. So earnings are normally distributed with a mean of 39,400. So if we have this normal curve, this normal curve, so something like this, with a mean at 39,400, we are looking for, and let's say this is 60,000 here. We are looking for the percentage of people who lie here. Okay. And so, well, how are we gonna get this? Well, what we always want to do with these types of questions, where we have a normal distribution, we want to turn it into a standard normal. So the standard normal is the curve, it's the distribution that has, so it's the normal distribution with mean 0 and standard deviation 1. So the one that you're all used to, that the log tables are based off, so it has a mean of 0 and standard deviation of 1. Okay, so we want to change it to be in this form because we know how to read this. We know how to, we have log tables for when it's like this. And how we change that is with this formula. That's what this formula does. It gives you a z-score in the standard normal. So we want to turn what we have into the standard normal because we know how to work with that. Okay, and so if we plug in, we want to see, well, what is 60,000 on this normal distribution? What is that equivalent to here? So it's probably something around, something around here. Okay, so if we plug in 60,000 into this formula, minus 39,400, and divide by the standard deviation, then we get a z-score of 1.594. Okay, so we have our z-score of 1.594. So if we go to the log tables will give us the proportion or the percentage of people, proportion of z below 1.594. So that's the percentage of people who will have a z-score below 1.594. So that's all these people here. Or equivalently, the percentage of people with an earnings of less than 60,000, these people here. And if we go to our log tables, so we're looking between 1.59 and 1.6, we get somewhere around 0.9445, something like that. Okay? And that's the percentage of people below 60,000. So the percentage of people above 60,000 will be just 1 minus this. 1 minus 0.9445. And this will just give us 0.0555. So the percentage of people is 5.55%, approximately, something like this. This is the percentage of people who are earning 60,000 or more. And because it's to the nearest percentage, or the nearest decimal point, it's around 5.6%. Now on to part 2. The government will also provide a subsidy to the lowest 10% of income earners. Find the level of income at which the government will stop paying the subsidy. Correct to the nearest euro. Okay, so what is it that we're looking for? So if we have our distribution of earnings, which is normally distributed, so with a mean of 39,400, we are looking for the earnings X such that 10% of people, so this area or this percentage, earn less than X. So we want X such that 10% of people earn less than X. And so really what we're trying to find is this distance of the bottom 10% to the mean. Okay? And the distance from the bottom 10% to the mean is the same distance as from the mean to the top 10%. So the top 10% of earnings are just as far from the mean as the bottom 10%. And what that sort of means is, so if we let this be y, the earnings at which 10% or more, then y minus 39,400 is equal to 39,400 minus x. They're the same distance. And the reason for that is the normal distribution is symmetric about the mean. So it's like a mirror image across through this line. Okay, so what we're looking for, what's equivalent to what we're looking for, we want y such that 10% of people earn more than y. And you might be thinking, well, if it's the same thing, then why would we look for y instead of x? And the reason why is that it's actually much simpler just from the way that the log tables work with the normal distribution. So we'll see this in a bit. Okay. So now we're looking for the corresponding z-score to y. So if this is our standard normal distribution, what is the value of z that corresponds to y? What z corresponds to y? Or in other words, what value of z is greater than 90% of values? And so what I mean by that is, what's the value of z? So if this is the top 10%, well then this, the rest, should be the bottom 90%. So for what value of z is 90% less than? Okay, and we actually have log tables for this. So if we have this probability of a z-score being less than z is 0.1, well, we can find this value of z. We just look for, sorry, not 0.1. The probability that z is less than z is 0.9. The probability of z is greater than z is 0.1. But we have log tables for this. Okay? And so if we look for 0.9 on the log tables, it's right around 1.28. So z equals 1.28, approximately. So our z is 1.28. So if we use our formula z, because we want to bring this z back to this y, z equals y minus 39,400 over 12,920. And now we can find what this value of y is. The value of y such that 10% of people earn more. And so this equals 1.28. So if we multiply by 12,920 by 1.28 and then add the 39,400, we get 55,937.6. Okay, so that's the earnings that 90% of people earn less than. So this is this earnings y. And we remember this equation, y minus 39,400 is equal to 39,400 minus x, the difference from the mean. The difference of the bottom 10% to the mean is also the difference from the top 10% to the mean. So now if we use this formula, so 55,937 minus 39,000, sorry, 0.6 minus 39,400 is equal to 39,400 minus x. So then we can solve for x, and we get 39,400 times 2, because we would bring this over and then bring this over, so we get 2 of these. and then we bring this over, and we'd get minus 55,937.6 equals 22,862.4. They set to the nearest euro, so 22,862 euro. So anyone who earns less than or equal to 22,862 euro will get this subsidy. Now on to part 3. Sometime later, a research institute surveyed a sample of 1,000 full-time workers, randomly selected, and found that the mean annual income of the sample was 38,280. Test the hypothesis at the 5% level of significance that the mean annual income of workers has changed since the national data were published. State the null hypothesis and the alternative hypothesis. Give your conclusion in the context of the question. Okay, so whenever we're working with a hypothesis test, we want to start off with our null hypothesis, which is essentially that there is nothing interesting to report. So nothing interesting to report would just be that the mean hasn't changed. So the true mean is still 39,400. And then the alternative hypothesis is always something interesting to report. So in this case, the mean has changed. In other words, the mean is no longer 39,400. Okay, and so we're working at the 5% level of significance. 5% level of significance, which means that to reject our null hypothesis, to conclude something new, we have to be 95% sure. We have to be 95% sure that the null hypothesis is false. Need to be 95% confident that H naught is false. And so, well, you might read there 95% confident, and the first thing you might think of is sounds like a confidence interval. And so we want to be 95% confident that the true mean is not 39,400. So if we do, so we have this sample mean, this x bar equals 38,280, and a sample size of 1,000. And so we want to construct a 95% confidence interval for the mean. Okay, so we have our formula for the 95% confidence interval. It's the sample mean minus 1.96 times the standard deviation over the square root of n, the sample size. So that's the lower limit. And then the upper limit is the sample mean plus 1.96 times the standard deviation over the square root of the sample size. Okay, so if we just fill this in, we will get a confidence interval, a 95% confidence interval, sample mean 38,280 minus 1.96 times the standard deviation, 12,900, and actually, let me just write this a bit bigger. 12,920 over the square root of 1,000. And then our upper limit is 38,280 plus 1.96 standard deviation over the square root of 1,000, the sample size. And so if we plug this into our calculator, we will get a 95% confidence interval of 37,479 euro and 21 cent. That's our lower limit, and our upper limit of 39,080 euro and 79 cent is our 95% confidence interval. Okay, so what a 95% confidence interval means is that we are 95% sure that the true mean lies between these two values. So is less than the true mean is less than 39,080.79 given a sample mean of this. So we're 95% confident that the true mean doesn't lie in here. And so that means that we're 95% confident that 39,400 does not lie in here. So we're 95% confident that mu does not equal 39,400. And so that means we reject the null hypothesis. We're 95% confident that 39,400 is not the mean because it does not lie in our confidence interval. And so if we say this formally, we reject H naught, that the mean, let's just write this out, the mean income remains 39,400. And conclude that we conclude the alternative hypothesis, that the mean income has changed. And it's always important to write your conclusion in the context of the question. So not just we reject H naught and conclude the alternative, because that doesn't really give you any information about what it actually is that is being concluded. Now on to part B of this question. The Research Institute surveyed 400 full-time farmers randomly selected and found that the mean income for the sample was 26,974 and the standard deviation was 5,120. Assuming that annual farm income is normally distributed, create a 95% confidence interval for the mean income of full-time workers. Okay, so this should be nice enough. Let's just write down the information they've given us. So a sample size of 400, so our n equals 400. A mean income, a sample mean, not a true mean, sample mean of 26,974, and a standard deviation of 5,120. Okay, so as we talked about in the last question, we have our formula for a 95% confidence interval with a lower limit of the sample mean minus 1.96 times the standard deviation over the square root of the sample size. That's our lower limit. And then an upper limit of the sample mean plus 1.96 times the standard deviation over the square root of the sample size. And so now we can just fill this in very nicely. 26,974 minus 1.96 times 5,120 all over the square root of 400. And then 26,974, our sample mean, plus 1.96 times 5,120 over the square root of 400. And now if we just plug this into our calculator, we'll get 26,472.24 as our lower limit, and 27,475.76 as our upper limit. So our confidence interval for the true mean is 26,472.24 and an upper limit of 27,475.76. Now on to part C. It is known that data on farm size are not normally distributed. The Research Institute could take many large random samples of farm size and create a sampling distribution of the means of all these samples. Give one reason why they might do this. Okay, so sort of the trick here is whenever you have a non-normally distributed, a non-normal distribution, you should immediately think of the central limit theorem. And the central limit theorem essentially says that even if you have a distribution that isn't normal, if you take sample means from that distribution, so you take a sample from that distribution and you find the mean, that those means that you get, those sample means you get, will be normally distributed. So the central limit theorem, the sample means from any distribution are normally distributed. And this is an extremely important theorem in statistics and maths as a whole. And so the reason that they might do this is so they can work with a normal distribution. So they can work with, because we have all these tables for normal distributions. Normal distributions have all these nice properties. Or so they can work with normally distributed data. like the way we do confidence intervals is based on normal distributions. It's a lot more difficult to do a confidence interval with a non-normal distribution, and it might even be impossible. Normally distributed data. Now on to part D. The Research Institute also carried out a survey into the use of agricultural land. N farmers were surveyed. If the margin of error of the survey was 4.5%, find the value of N. Okay, so this is just one of those questions where you have to know a particular formula. So we have this formula for the margin of error of the survey. Margin of error of a survey let's call it E, is equal to 1 over the square root of the size of the survey. And this is just something that you are going to need to know. They do ask it sometimes. Okay, so E equals 1 over the square root of N. So in our case, the error is 4.5%, or as a number, 0.045. And so then we have to solve for N. So 0.045 equals 1 over the square root of N. And so if we multiply both sides by the square root of N and then divide by 0.045, so the square root of N and 0.045 switch places, we get square root of N equals 1 over 0.045, and then we square both sides to get rid of the square root, and N equals 1 over 0.045 squared, which equals 493.83. But of course, this is N is number of people, so it can't be like a 0.83. You can't have 0.83 of a person. So we'll just round this up to 494 people.